Hey guys, it's Miss Johnson, and I'm here to bring you our notes for Unit 3, Notes 3, which is on the addition rule. The addition rule of probability is used when we want to find the probability where we have multiple successes. So if we are asked to find the probability of this or that happening, that means that we have multiple successes going on. So when we have multiple successes, we're finding one probability, but there's more than one success. We need to take those probabilities and we need to add them together. So the addition rule looks like this. If we have the probability of A or B, that means that A is a success or B is a success. That's where we get that word or. That tells us that we have to add our probabilities. That gives us the probability of A plus the probability of B, but we're going to have to just subtract some things out sometimes. So that's what we're going to talk mostly about today. So one probability is what we're finding, but it has multiple successes. So let's talk about the difference between mutually exclusive events and inclusive events. Mutually exclusive events are events that don't affect each other. An example of that is rolling a 5 and rolling a 2. Rolling a 5 has one success, a 5, and rolling a 2 has one success, a 2, and those two probabilities or those two events don't have any crossover. They don't have any results that could happen in both categories. When you want the probability of rolling a 5, your only option is a 5. Rolling a 2, your only option is a 2. They don't affect each other. When we talk about inclusive events, we could look at, these are events that do affect each other. These are events that do have crossover, or they do have things that exist in both categories. So for example, rolling a number less than 3 and rolling a 1. A number less than 3 is a 1 or a 2. So there's two successes for that probability. Rolling a 1 is just a 1. There's one success for that probability. But the problem here is that if we take those two and we add them together, this 1 existed in both categories. I can't add the 1 twice. The 1 doesn't exist twice on a number cube. So I have to subtract away the things that existed in both categories. That's what's going to happen with our addition rule today. So we're looking for one probability, but it has multiple successes. Let's do some examples here. It says, in a recent study, it was found that 63% of all University of Minnesota students read Time magazine, 51% read U.S. News and World Reports, 24% read both. That's a good thing to know. If a student is randomly selected, what is the probability that the student reads either magazine? So the probability that a student reads Time or U.S. News and World Reports looks like this. It's the probability that a student reads Time plus the probability that a student reads U.S. News and World Reports minus the probability of what I like to call both. Okay, or in other words, minus the crossover. Because if I am a person who reads Time magazine, that means that I fall into this 51%. But I could also be a person who reads U.S. News and World Reports, or sorry, I fall into that 63% who read Time. I could also be a person who reads U.S. News and World Reports who falls into that 51%, but I am only one person. So I got counted in the 63%, but I also got counted in the 51%, and that's not okay. You can't count me as a person twice. You can only count each person one time. So that's where this 24% who read both comes into play, and we have to take that away. So in this case, the probability who read Time magazine is 61%. I can't read today. 63%. The probability who read U.S. News is 51%, and the probability who read both is 24%. If you don't have your calculator out yet, go ahead and grab that now. I'm going to type mine in, 63 plus 51 minus 24, and that gives me 90. So that means 90% read either magazine. That's what we're looking for here. What's the probability that you read Time or U.S. News? Okay, let's take a look at the next one, example 2. 50% of all students eat pizza for lunch, 10% of all students eat carrots for lunch, and 3% eat both. What percent eats pizza or carrots? So I'll use my son as an example here. He's definitely a kid who would eat both. He would love to have pizza for lunch, but he also eats carrots for lunch pretty much every day. He likes carrots. So if he gets counted in this 50%, but he also gets counted in this 10%, that means that we counted him twice. So we can't just take the 50 and the 10 and add them together. That's not going to be okay because now we've counted some people twice. So we have to make sure that we account for those that were in both categories. So the probability that a student eats pizza or carrots for lunch is the same thing as, or is written out as, I should say, sorry, I meant to write an equal sign there, is the probability of a student eating pizza plus the probability of a student eating carrots minus the probability of the people who eat both. So in this case, the kids who eat pizza are 50%, the kids who eat carrots are 10%, and the kids who eat both are 3%. So that 3% of kids are the kids that got counted twice. Can't count them twice, so we have to subtract them away. So 50 plus 10 minus 3, that's 60 minus 3, which is 57. So 57% eat pizza or carrots. All right. Let's take a look at the next one. So it's great and fine when you have percentages written out for you, but that's not always the case. So just keep that in mind. In this one, it says 74% of high school students take math, 50% of high school students take science, 40% take both math and science. What percent take math or science? You maybe haven't seen this, but at the bottom of this page, I have our little equation written out here. So I'm going to drag this up to the top for this one because I want to see what information we have given here. So here's my addition rule. I've got the or over here. I've got the probability of A, the probability of B, and the probability of both over here. Now, in this question, we have 74% for those who take math. So probability of math plus the 50% who take science, probability of science, minus probability of both. So that looks like 74% plus 50% minus the 40% who take both. So the probability that somebody takes math or science, 50 minus 40 is 10. So if I add 10 to the 74, I've got 84% take math or science. Science I can spell. Okay. Let's take a look at example 4. 42% of all senior boys play football, 7% of all senior boys play chess, 47% of all senior boys play football or chess. So again, I'm going to drag out my rule here. You guys, I can't stop yawning today. I don't know what my problem is. Okay, so here's my rule. And again, let's look at the information that we have. We have 42%. So in this case, if I do probability of football or chess, that means I'm looking at the probability of football plus the probability of chess minus the probability of both. Okay, so 42% of all senior boys play football. That's this right here. 42%. 7% of all senior boys play chess. That's this right here. 47% of all senior boys play football or chess. Be careful here. You're given the or. You are told that this is 47. The question is, what is this? That's our question mark. That's our variable. That's what we have to solve in this case. We're given the or, we're trying to find the and. Here's where good old algebra is going to come into play for you. So I'm going to call that an x, and I'm going to solve for x here. If you remember solving for x, we can put these two things together. So I have 47 equals 42 plus 7, which is 49, minus x. I'd subtract my 49 here, and I'd get negative 2 equals negative x, which obviously we all know, divide by the negative 1, divide by the negative 1, x equals 2. So 2% play both is what you were looking there. Okay, so this was just a case that we were given different information. We used the same equation, but we were given different information. So we had to solve for this both part over here on the right. Example 5, it says calculate the following probability. 25% of students run 2 miles a day, 30% of students weight lift a day, 48% run 2 miles or weight lift. What percent run 2 miles and weight lift? So again, if I pull up my little model here, this is my model or my equation, if you will. Let's look at what we are finding. We've got the probability of running or weightlifting. So why do I keep putting a plus sign there? Is equal to probability of running plus the probability of weightlifting minus the probability of both. In this case, I'm given 25% of students run, so that's 25%. 30% of students weight lift, so that's 30. And 48% of students run 2 miles or weight lift, so that's 48 over here. And again, we're looking for the and. So good old algebra, solve for x, solve for what's missing. 25 and 30 is going to be 55. So 48% is equal to 55% minus x. Subtract your 55 there. 48 minus 55 is going to be -7. So -7 equals -x. Obviously, divide by the -1 gives me x equals 7. So 7% do both activities. Okay, so again, this was another case where we use the same model because we were given the or. If you're given the or, you can use that to your advantage. So we use the same model, but we're missing different pieces. We're missing the and in this case, so that's what we had to back out and solve for. All right, so now let's set up some other probabilities where we have to actually find the probabilities ourselves. So in all of those first few examples, we were given the percentages. In these, we have to set them up ourselves. So the first one, it says the probability of a red card or a jack. So if you go back to that standard deck of cards that we have, a red card or a jack, I'm looking for the probability of red plus the probability of a jack minus the probability of both. Here's the thing. Now, we talked about mutually exclusive events at the beginning of the lesson. There are times where this probability of both is going to be 0. There's times where you don't have anything that crosses over, okay? If that is the case, that's fine. You can just fill it in with a 0. My suggestion to you is to always put this probability of both piece in, even if you're going to fill it in with a 0 probability. But then you don't forget about it. So many times kids forget to subtract the duplicates. Then they're counting cards twice, and that's not okay. You can't count a person twice. You can't count the same card twice. You can't count the same outcome twice. So if you always list the both, then that always gives you a spot to take those pieces away, and then you can just always remember to account for that. So if I take a look at the probability of a red card, there's 26 out of 52 red cards. Probability of a jack, there are 4 jacks out of 52 cards. And then the probability of both. So now here's where you have to ask yourself, how many jacks are also red cards? There's 4 jacks, 2 are black, 2 are red. So there were 2 red jacks that got counted here and also got counted there. So I need to subtract 2 away. So 26 plus 4 is 30. 30 minus 2 is 28. I get 28 out of 52. I'm going to plug that in and round to the nearest thousandth place. 0.538 there is my probability. You get a decimal of 0.5384661 ... goes on. And remember that in probability we use the fourth to round to the third. So 0.538 is my answer there. Sorry, that got a little messy because I kind of ran out of room on that side. Okay, let's do probability of diamond or 5. I'll come over here so I have some more space. So probability of diamond plus the probability of a 5 minus the probability of both. So in this case, Diamonds, there are 13 of each suit, so 13 out of 52 for diamonds. Fives, there are 4 of each card, so 4 out of 52 for the fives. Now the both. There's a 5 of diamonds. There's a 5 of diamonds, which means that that 5 of diamonds got counted here with the diamonds, and that 5 of diamonds also got counted here with the fives. That's not okay. The 5 of diamonds is only one card. You can't count it twice. So since I can't count it twice, I need to take that one card away. So I end up with 17 minus 1, which is 16 out of 52. That gives me a decimal of, if I plug it in, 0.307, 3076923 ... Use the fourth to round to the third, you get 0.308 for your probability there. All right, next one, diamond or a non-face card. Ooh, that's a tricky one. Diamond or a non-face card. Don't forget to take into account that non in front of there. So probability of diamond plus probability of non-face card minus the probability of both. Okay, so diamonds, there's 13 out of 52. Non-face cards. So if we think about face cards, this is kind of like a complement probability. Face cards, there are 12 of them. There's 3 in each suit. 3 times 4 is 12. Okay, there's 52 cards total. So if I take 52 and subtract the face cards, that gives me the non-face cards. 52 minus 12 is 40. So there's 40 cards that are non-face cards. Okay, so now let's talk about the both. In the both category in this one, I'm thinking of only that row of diamonds, okay? So if I look at that row of diamonds, there are 3 cards that are face cards. There's 13 cards total. That means that if I take those 3 face cards away, there's 10 cards that are non-face cards. Okay, so there's 10 cards that are non-face cards that are also diamonds, which means they got counted twice. They fell into the diamond category, but they also fell into the non-face card category. So I have to take those 10 cards away because those 10 cards don't actually exist twice. I need to account for that. So I have 13 plus 40 minus 10, which gives me 43. So I have 43 for my probability there. 43 out of 52. Oops, 43 divided by 52 is 0.827. So I get 0.826923. And then this 9 is going to tell this 6 to go up. So I have 0.827 for probability there. We're going to skip this example for now, and that's our last one. So thanks for listening today. Don't worry about that last example. We're not going to do that one today. Don't forget to hop in and do your practice assignment, and let me know if you have any questions. Thanks for listening, and I will catch you next time.